and it all looks nice and it's, you know, catered to me. I'm like, that's fine. I'm a guy who like.
All right, so today's video is all going to be sideways. Usually rebooting it fixes that, but now that Brooke's gone, I'm ready to answer a question. All right, are there any questions on the chapter 3 textbook? Okay.
In the homework problem, question 10.
Number 10. We'll think we get that. Okay. Given the magnitudes of the velocities, I assume it's total. Find the components of v total along the x and, oh wait, no. Oh, find the magnitudes of velocities va and vb. Okay.
How do you get to 0.3345 VB? It says dividing equation first by 0.9 gives 4.7 ms.
You're looking at the solution right there, I'm assuming? So you were looking specifically at, divide the equation by, okay. That's just the math aspect of it. Is the question only about that piece?
Yes.
Okay, so you're good up till then?
0.3345, yeah.
I'm gonna do sort of an analog of that. It's not this specific one. If that works for you, if not, I'll go back and do something more sophisticated. One there. All right, so you have the initial velocity, you have the total velocity, or this total magnitude of the vector, and you have the direction that you can just add those two angles together. So since you have the total, I think they label it as v total, and you have that angle right there, you can break it into components, so you know what the total horizontal and the total vertical is. And that's comprised of some bit there and some bit there. And you can break each of those down into its parts. Sort of recap, this was not where you had the issue, but I'm just going to call this A, B, C, and D. We're trying to find those pieces. I know that A plus C is equal to whatever that total length is there. I'll do something called like X, we'll call that whole thing Y. And B plus D is equal to Y. So that plus that is equal to the whole thing. A is going to be some, it's basically I have this, call it V1, theta 1. So A is V1 cosine of theta 1. C is going to be V2 cosine theta 2 is equal to whatever this whole thing is. Since we're trying to find V1, basically, or sorry, if it doesn't throw you, they use VA and VB. We have the angles, so this is a number. That is a number, it should be a 2 right there. So in essence, once you find the cosines here and the sines down here, you're going to end up with, and I'm just going to make up a number, say 0.9 times V1 plus 0.7 times V2 is equal to 14. And then from the other equation, you might end up with, say, 0.2 V1 plus 0.4 V2 is equal to 13. We have two equations, two unknowns, which is what they have right before they do the divide by. And the question is, how do you solve it? What they did is they took one of the coefficients and said, hey, let's just divide by that coefficient. So if we divide both sides by 0.9, this becomes V1 plus, I guess it'd be 0.7 repeating V2 is equal to whatever 149 says. Then if you solve for V1, by bringing that over, you can now plug that into here and solve for V2. I skipped a couple of steps there, but does that cover what your question was, or do you need me to be more specific to
Yeah,
this
I
problem?
got what you mean, but, the 0.3, so they got the 0.3 by just dividing them?
So if you take looking at equation I there, the 0.3090 or the 0.3345?
45.
All right, they got that by doing the 0.3090 divided by 0.9239. Assuming they didn't make a careless error. Does that answer your question? Okay.
I may have missed that last part. Did you say that they used, instead of 0.7 V2, they would just use the 140 over, I'm sorry, 14 over 0.9?
Instead of doing what?
What,
What did I do?
when you got to the last part, 140 over 9, did you divide by 0.7 after you found that number, and then you would use that for V?
All right, so I originally had it set it equal to 14.
Right,
I divided by 0.9 to get rid of that coefficient.
right,
And so 14 over 0.9 is 140 over 9.
right.
Okay.
So then V1 is equal to 140 over 9?
Minus 140 over 9 minus 0.7 repeating V2.
So then you'd plug that in for V1,
Yep, plug that in for V1.
find V2 based off of it?
Yes.
Okay, just making sure.
Other questions on number 10? Yeah, 10.
So how did you, add the V1 and V2? Like 0.9 V1 plus 0.7 V2? And it says divide by 0.9?
All right, so once we get to this point right here, I got the two equations, two unknowns. There are a slew of math techniques to solve it. One of which is to solve for one of the variables in one of the equations, and then substitute that into the second equation. That's the technique that they're outlining here. So they just said, oh, let's just solve for V1 in the first equation, or VA in the first equation. And so they could have just as easily solved for V2 here, or V1 there, or V2 there.
But when they divide it by 0.9, they get 0.3345. So how did they divide that equation with 0.9?
Oh, the question is, I'm dividing by 0.9?
Yeah.
I made these numbers up here.
So you're dividing 0.9 V1 plus 0.7 V2 by 0.9.
Sorry, I missed the last bit.
Dividing the 0.9 V1 plus 0.7 V2 by 0.9.
Yes. You divide each of the terms by 0.9. You divide that by 0.9, that by 0.9, and that by 0.9.
So you don't add first, then divide?
I can't really add them because I've got these two variables tacked on there. Yeah, all I can do is, there's a plus sign in between them. That's as far as I can go without doing more manipulation. Is that? Okay. Other questions on this?
Yeah, on 52, I have a question on
Wait.
52.
Any other questions on this one before we do 52? And I think Brooke also has a question. Right. 52?
Yeah, so it's 52B. So when Allen encountered a headwind averaging 2 meters per second like, how would that headwind impact your answer?
Alright, so Brian Peddle is a human-powered aircraft across the English Channel. He flew 169 minutes at an average velocity, direction 45 degrees south of east. Alright, so 45 south of east. Alright, so he's basically moving in that direction. 3.53 meters per second. East, north, we'll make this positive. What the heck, we'll make them unit vectors. And this angle right here is 45 degrees. Alan encountered a headwind 2 meters per second, almost precisely the opposite direction of his motion relative to the Earth. What's his average velocity relative to the air? This gets back into the Galilean relativity. Let's go back to the car analogy. I have a car cruising down the highway at 50 miles per hour. Typically, 50 miles per hour, when you're talking about a car going that fast, that's relative to the Earth. It has to be relative to something. Relative to the people in the car's not moving at all. It's the Earth that's moving backwards. Oh, we're gonna run into the same issue I ran into before. Just a second, I want to make sure I don't have a minus sign in the wrong spot, the way I was about to explain it. Ultimately, the question was average velocity relative to the air. Oh, okay, nope, that works. I'm assuming that the headwind is not affecting that. He is going 3.53 meters per second. That is how fast he's going, and the wind is going 2 meters per second opposite him. It's not affecting that 3.53. That's the assumption I'm making here. So if you're in a car's going 50 miles per hour, this is the velocity of the car relative to the Earth. And so when you see this notation, the first subscript is the object, and the second one is the respect to. This is the thing assumed not moving. Because when you talk about the car going 50 miles per hour, we are not doing that relative to the sun or relative to the moon. It's relative to something that is still. If I throw an object, I'm in the back of apparently a really tall van here, throwing an object up front, if I throw it relative to me, so the velocity of the ball relative to me is 30 miles per hour, then someone on the side of the road is going to see that ball going how fast?
Faster? Like, a lot faster than what it would.
Well, we can be more specific than that.
Would it be 80 miles per hour?
It would be 80 miles per hour. If you have someone just standing here on the side of the road, a really tall person, if that's a car, then it's how fast the car is going plus how fast the car is going relative to the Earth plus how fast the ball is going relative to the car. I am making the assumption that I am going the same speed as the car. Why don't I change that to DC? So the velocity of the ball relative to the Earth is the velocity of the ball relative to the car plus the velocity of the car relative to the Earth. In Galilean relativity, this is a basic structure here. When you're doing one thing with respect to another, as long as those are the same, it's valid. So in the case of this problem, we have the velocity of, I guess, the aircraft relative to the Earth. That's 3.5 meters per second at a 45 degrees south of east. We have the velocity of the wind with respect to Earth, which is 2.0 meters per second, 45 degrees north of west. Because they said, pretty much in opposition to what he's doing. And the question is asking, what is the velocity of the aircraft with respect to the wind? This is what we're trying to figure out. Well, we need to come up with some sort of convention. It's a one-dimensional problem. So, or if you prefer, we can use I-hats also. But I'm just gonna make the direction he's going in positive. So this velocity here is positive 3.5 meters per second. This velocity here is negative 2 meters per second. Basically, instead of sticking with this coordinate system right here, I just tilted it. Which is one of the reasons I try not to use X hat and Y hat. So, I need to somehow combine these three things. So the acceleration of the aircraft with respect to the wind would be the velocity of the aircraft with respect to the Earth, plus the velocity of the Earth with respect to the wind. I got those two things right there are the same. This is good in Galilean relativity. Well, that number I have, that's 3.5. But this one, this is reversed. This is the velocity of the wind with respect to the Earth, and I want the velocity of the Earth with respect to the wind.
But that's fine, because of the Galilean relativity. Are we gonna need to know that for a tester?
Yeah, I was just gonna ask that.
All right, well, let's finish this and then we'll talk about need to know. All right, so right now, from Jacob's point of view, I'm coming at him at, we'll just say 100 miles an hour.
Whoa.
That's pretty intense. Okay.
Going in that direction.
Yeah.
From my point of view, he's coming at me at 100 miles an hour. What's the difference in the vectors of the velocities?
They're facing opposite directions.
And how do you represent opposite directions in?
Positive and negative.
So that's 3.5 minus V of WE. So if I flip the directions, it becomes negative. So this becomes 3.5 minus negative 2, or 5.5 meters per second. That's how fast the aircraft's going with respect to the wind. Assuming that 3.5 meters per second has already taken the wind into account. As opposed to it's not slinging down anymore. I forgot what the original question was. Was it just 52 in general, or?
Oh no, it was just
How to deal with the relative?
yeah, like with what our answer would look like with the 2 meters per second headwind.
Okay.
And yeah, you answered it.
All right. So now the second question of, do you need to know that? Not as explicitly now. When we get to, well, in 152, when we get to special relativity, and we find that this doesn't always work, at that point we'll come back to this. Hopefully that was vague enough, but specific enough to satisfy your needs at the moment. Yes, Brooke.
Okay, question 65. An athlete crosses a 25-meter wide river by swimming perpendicular to the water, yada yada. It asks, what is the speed of the swimmer with how fast is the water in the river flowing with respect to the ground, and then it asks what the speed of the swimmer is. I understand how you get, like, the angle that he's going at, but how do you get, like, okay, how do you get the speed from this? Are we using, like, archaic formulas here?
Let's see, 25 perpendicular to the water current, at a speed of 0.5 meters per second relative to the water. All right, so he's going 0.5 relative to the water. He reaches the opposite side, distance of 40 meters downstream from the starting point. Yes, you're using the cake formulas, but we can narrow it down even more than that, because I can't remember what this, how the solution writes it out, but acceleration is 0.
Right.
It's not just constant, it's a constant 0. So this is my river here, 25 meters across. He's swimming this way and he ends up down here. He is, lost it. So he's swimming 0.5 meters per second relative to, or, 0.5 meters per second relative to the water. I guess that's the velocity of swimmer with respect to water. So in essence, given he's traveling 0.5 meters per second this way, the flow of the water this way is not affecting his speed in that direction. So the time it takes him to cross the river is irrespective of any speed of the water, as long as the water is flowing perpendicular to his movement. Similar to when you projectile motion problems, the horizontal component, the horizontal velocity is not affected by the acceleration due to gravity because that is perpendicular to it. Similar here. So just from the fact that he's traveling a half meter per second for 25 meters, that tells you how much time is going, how much time. And then once we have that time, we can figure out how fast the water must be traveling. So yes, we are using cake formulas, but with acceleration equal to 0, we have displacement